Hey everybody, this is a Group 15 TC analysis. My name is Stephen Winter, and
I'm Brandon Zuniga.
My name is Fernando Montes.
I'm Haley Weitzman.
I'm Hunter Anderson. And I'm David Borhome.
And let's get started. Enjoy the show.
So to begin this project, we're given a set of data between the year 2000 and 2003 regarding total coliform at and around the Santa Ana River. So this data was divided up between along the shoreline north of the river, at the river's opening, and south of that river. And here we took that data and we plotted it given its location. On the left we have a CDF for data north of the river, and here is a CDF for data south of the river. We took that data and we fit it to an analytical graph, and we found in both of these situations a normal distribution worked best. And at the river, we also had data, and we fit it with another graph where it also worked out where a normal distribution was best for that location, which is denoted here by a star.
So continuing with the log transform data, we took the original CDFs and plotted them against each other, with black being at the Santa Ana River, red being north of the Santa Ana River, and blue being at the Santa Ana River. Excuse me, black was at the south part of the river. So from this data, we concluded that you have the highest probability of finding low concentrations in the south part, or south of the river, which means you should probably recreate somewhere along the lines of Newport or anywhere else south of the river.
All right, and after comparing our TC data in a CDF, we compared and compiled CDFs for the temperature and salinity data. So this was our temperature CDF. You can see the blue is the empirical information, and from our MATLAB code, we used this CDF plot function to gather our mean and median, and also our standard deviation. And from there, we generated random values based on our stats10 function, and we created a random normal distribution from that, which fit the data pretty well. And we tried the same approach with our salinity CDF, but we found that using the same normal distribution didn't fit the curve well. So our second approach was to use an extreme value distribution with the normal distribution parameters, which also did not fit the curve well. So eventually our third trial was calculating the mean and standard deviation and fitting it to an extreme value curve using our altered parameters, which fit the curve pretty well.
So one of the other data points that was also given was the ocean temperature of whenever that data point was taken. So ocean temperature does vary depending on the time of year. When it's in the summer, it's going to be warmer. When it's the winter, it's going to be colder. So we analyzed the TC based off of this warmer or colder, essentially. So we started out with a middle point-ish of 16.74, and we did some analysis. You can see here that the probability of TC being greater than 10,000 at the Santa Ana River is pretty different, or slightly different, about 1% of difference between the probability of TC being greater than 10,000, conditioned that the temperature is higher than 16.74. And so then you can also see here, we increased the temperature, or the temperature boundary. So if the temperature was higher than 17.74 and then 18.74, there was a slight increase between 0.518 and then 0.80. And then there were no data points above 19.30, so there was a zero probability of that. We also did it the opposite way, so we went down. So we went to 14.74, then 13, then 12. We can actually see here, however, that the probability is increasing as the temperature gets colder. So that begs the question: why is the temperature, or why is the TC probability, or the extreme value TC probability, higher when the temperature is colder? So it might be that the TC probability is higher in the winter. It might be because of storms, extra runoff. We're not quite sure, but there is some sort of significance that the temperature has an effect on the TC content.
Next, I'd like to talk about periodic temperature. As you can see with the regular temperature, there was significant statistical data based off of how the temperature varied, but for this one we want to actually see because as the the year goes around, the temperature goes from highs and lows, so we want to see like if there's a deviation from like the expected value. So we decided to plot all the data points, and so as you can see, it's a kind of like a shiny soil curve. So as you go, we got like high points during summer months like June, July, August, and cold points January, February, March. And then we wanted to fit a sinusoidal wave. So we used those parameters in order to find the sinusoidal wave. We picked a couple points, plugged in, found the amplitude and the phase shift, and we got this formula. And the beautiful graph that follows, nice red graph that kind of follows it. So this is our periodic temperature, and now we want to analyze if there's a deviation from that expected temperature given that time period. Is that going to make a difference on the TC being greater than 10,000? So our results are if the deviation temperature is greater than 1, and we got about 2.2% compared to just the regular probability of temperature or TC greater than 10,000, we're about 2%. So there's not much statistical difference there. Let me go back a little bit. And as you can see, the more deviation it gets, the lower probability. And I kind of want to conclude or come to like hypothesis that as the temperature deviates from normal, you're going to get less probable because basically there's more plot points along the temperature or the expected periodic temperature. And then we're gonna do the same thing with the deviation temperature less than -1 degrees deviation from the periodic temperature. And it doesn't really increase that much. It increases a little bit up to, and then less than 3, less than -3, -0. So there's not much statistical data in regard to that. And then there's one more thing that is kind of interesting. So if we look at the temperature deviation between -1 and 1, we get 2%, and that is really close to our 1.97%, which shows that basically the deviation, as the deviation is closer to the periodic temperature, you're going to get the same expected probability of the TC greater than 10,000. So it's kind of significant. And then next slide, we'll give it to David.
So then, look at the TC condition on location. Ideally, it'd be important to determine the probability of TC greater than 10,000 based on the location from the Santa Ana River outlet. We could hypothesize that the probability would be greater closer to the river outlet if the outlet is the main source of the TC. So first we took a look at the 15 north station and checked the probability of the TC being greater than 10,000, and we came to the conclusion of a 9.68% probability. And we start to see a trend. The closer you get to the station, the higher the probability would be. You can see that the probability at 3N is 41.94%, and much greater than at 9 north station. And then we took the probabilities from the south stations as well, and the same trend appears. The closer you are, the higher the probability. For example, 3 south, probability is 35.48%. All of these probabilities did not add up to 1, and the reason for that being is it is not mutually exclusive. So you could have a TC being greater than 10,000 at all the stations.
Now let's talk a little bit about the salinity and the TC and how they're related. So if we just took a look at the probability of the TC greater than 10,000, we're roughly about 5% for that to happen. But as you condition it off the salinity, for example, we picked the mean salinity. So if it's conditioned off the mean salinity, anything less than that it's around 10-11%, which is about double what it normally is. And then as you decrease salinity, it increases from about 60%, less than 32.5, and then less than 32, 75%, which is significant increases. So, so that means that the hazardous TC in the ocean is highly correlated to the salinity. And so it's not necessarily causal, but it is related. And we want to take a little bit of a closer look, like why is the salinity related to the TC? And our hypothesis is that as the Santa Ana River flows into the ocean, it dilutes the ocean, but it also brings in TC with the river. And then another thing we want to look at is why is there more water flowing in? It's probably, our hypothesis is that the rain, when it's raining, there's higher flow from the Santa Ana River. So we went back and gathered precipitation data for the 3 years that we were studying. And we found that, so we conditioned the TC greater than 10,000 off of or given the fact that it's raining, and it increased from 4.5% to about 18%, which is about 4 times the probability if it's raining outside, you're going to have a higher percentage. And vice versa, given the fact that there's TC greater than 10,000, what's the probability that it's raining? It's about 41%. And compare that to just the probability of rain, which is 10%, it's about 4 times the probability given TC greater than 10,000. So it's a fair assessment to say that the rain and the TC concentration is highly correlated. And then one more thing to add. So we also wanted to condition the salinity and the precipitation just to see how they correlate, because that seems like more of a direct correlation. If you have rain flowing into the river, then it'll push more water into the ocean and diluting the salt water. So as you go down from our mean salinity, probability of rain is about 19%. Excuse me. And then if you're less than 32 salinity, then the probability of rain jumps up to 71%.
Finally, we can conclude that our approach to analyzing the extreme values. So in analyzing the extreme values, we wanted to focus on the high TC concentrations because this is what's concerned to the public with organizations that have to put out warnings for beach locations. So to analyze the extreme values, we subsampled 100 times to get a set of 100 extreme values. And we plotted this extreme value on a CDF. And using the method of moments, we found the parameters lambda and zeta, and from lambda and zeta, and n, which was our number of samples collected, or number of times sampled, we found un and an, which gave us our extreme value graph. So the most probable value in inverse dispersion, which was alpha n and un for the type 1 asymptotic distribution, could be transformed to the type 2 log normal distribution with the parameters bn and k. And from there, we can vary the values of n to find our most optimal fit curve. So these are the equations we used. We have our un equation and our alpha n equation using the lambda and zeta parameters. And from there, we can find bn and k from the un and alpha n values. And from there, we can plot it into our CDF graph using our bn and k values and y corresponding to the extreme values of the TC data. So this was our first step was plotting the data and then using multiple methods in MATLAB to calculate our lambda and zeta values. And from there, we can plot extreme value functions and see how well they fit the curve. So using Model 1 and Model 2, we gathered different lambda and zeta values and came to the conclusion that Model 1 fits our data the best. So from there, we used those lambda and zeta values and did calculations with the previous equations in the previous slide for our values we needed to graph the extreme value distribution with. And we found that varying the n value varies the graph. So first we started with n equals 100 samples, and then we went with n equals 1,000 samples, and then we found the perfect graph, which was n equals 200 samples. And using this graph, we can analyze the data further. We can analyze the median of the extreme values, but what we're really concerned with is how far the extreme values can go up the graph. So we realized that starting with the natural log of 7 going up to, or e to the 7th power going up to e to the 14th power, which is about 1 million units of TC, is a level of concern. And so using this graph, we can analyze the extreme value of the TC, or the trends of the extreme value of the TC. And in conclusion, to summarize our report, we came to a few realizations that Newport Beach is typically a cleaner beach than Huntington Beach. And while the temperature follows a normal distribution, the salinity tends to follow an extreme value distribution because of the high concentration of salinity values, or the common salinity value that happens, which is about 33 or 34 units. We also found that salinity and precipitation, as well as location, are highly correlated to TC concentration, but temperature is not a significant factor. And to conclude, we used the type 1 asymptotic distribution to transform into a type 2 asymptotic distribution to approximate the extreme value of the TC data so we could examine the trends of extreme value. Thank you very much.